my name is Ali Shirsavar. I have been working with Omicron for many, many years now, and delighted to be doing this presentation again, albeit virtual. Today, over the next 40 minutes or so, I'm going to talk about how to use off-the-shelf transformers in switch mode power supplies. I know that the audience for this particular symposium are already very experienced and experts. So this, however, is actually aimed at people who do not want to have their own custom transformers. So it's kind of aimed at engineers who are either new to power supply design or recent graduates, or people who just do not want to get their hands dirty with magnetics and they just want to be able to buy it. So if I go through, first of all, off-the-shelf transformers, understanding them, what are they? You can buy transformers from Vert, from DigiKey, and so on that are pre-wound. Each transformer comes with several windings. This is usually 6. Worth Electronics has got a flex range of transformers, and you can find them here. There are other magnetics manufacturers who also do them. The idea is that the user arranges these windings either in series and parallel to get the right inductance and the turns ratio that they need, and therefore they avoid having a custom-made transformer. So in all fairness, they will never perform, in my opinion, as well as one that you have custom wound. But the advantage is that you can you can buy it straight off the supplier. The leakage will not be as good, perhaps, may not have the exact turns ratio that you need, or the pinout may not be quite right. But wouldn't it be great if we could just order transformer along with the capacitors and all the other components? We think it's possible, provided that your application is low voltage, low power, let's say flyback or forward. In this presentation, we're going to talk about flybacks at the expense of some performance. So here's a data sheet of one of these off-the-shelf transformers that I downloaded from Worth's website. It's called a Flex Transformer. You can see that we have got 6 windings here. The product family is there. When I create a PDF, for some reason, this link breaks. So I do apologize. Just type in Flex Transformer Worth. You'll get to the right page. And we're going to show how we're going to use these in order to design our power supply. So as I mentioned, we have got 6 windings. The EFT15 and EFT20 range, they are arranged like this. They are in fact wound by filler. That's pin 1, that's pin 12, 2 and 11, 3 and 10, and so on. And given this setup, you can see that we can wire our transformer to have a fixed set of turns ratios. So how can we connect them? If I use, let's say, pin 7 and pin 6 here and here as my secondary, so that'll be the secondary winding, and then I connect pin 9 to pin 5, pin 10 to pin 4, pin 10 to pin 3, and pin 12 to pin 2, then I pin 1 and pin 8, pin 1 here, that is the top of my winding, and pin 8, which is the bottom of my winding, becomes the primary. And the whole thing will act like a 5-to-1 turns ratio transformer, and it will look like this. So I've created myself a 5-to-1 transformer. The inductance on the primary and the secondary, of course, is dependent on these, how they are connected in series and parallel. So is the amount of current that you can pass through it. So is the amount of saturation current that you have. So we're going to talk about all of this in a moment. Of course, there are many ways to wire these. For simplicity, just we have used it without any interleaving in order to make things quite simple. And please take a note of this dot convention, because I'm going to talk about this later. Okay, so if I have a transformer that is like so, I've got my primary, I've got my secondary. All I have to do to make a DC-DC flyback is to connect the pin 8 to my switch and pin 1 to my VIN, and then pin 7 to my diode and pin 6 to my secondary ground, and I have got a flyback. Okay, our choice is limited, so we can use off-the-shelf transformers if we can get the right turns ratio, we can get the right inductance, right? We can stay within the available rated current, and we can stay under the saturation current. So these are the criteria that we're going to meet in order to be able to just buy the transformer off DigiKey or whoever and not have to deal with winding our own transformer. The design's turns ratio and inductance can be really easily calculated. So when you're designing a power supply, either you're using a tool or a spreadsheet from the manufacturer, we have WDS, Worth has Red Expert. It gives you the inductance you need. It gives you the turns ratio that you need, or you can calculate it by using many of the fantastic books that are available. I know that Christophe Basso was the keynote. We're obviously delighted to see him present here. So he's got a fantastic book on how you calculate all of this. So let us assume that we have the inductance and the turns ratio and currents because you can easily calculate it. The actual inductance, what you're going to get when you get your transformer can either be calculated from the device datasheet, or I've created a spreadsheet which lists all the important ones. Right. So this spreadsheet you can download for free from the link that is available, and the WDS you can also download. We give everybody who's attending this webinar 6 months free license, so you can design your own flybacks. Okay, so in order to be able to use the off-the-shelf transformer, really, we need to follow 5 really simple rules. Rule 1, you can, of course, connect the coils in any which way that you like, but you must stick to the dot convention, right? So, for example, you cannot flip this the other way around. You cannot flip that the other way around. So stick to the dot convention that gives you the correct power supply. Then, what is the rated current that we can have? So the datasheet specifies something called rated current base, or IR base in RMS. This is taken from the datasheet of the device from Worth's website. For this particular device, you can see that is 1.91 amps. So if our secondary has got 4 parallel windings and each one can have 1.9 amps, then we end up being able to pass a secondary RMS current of around 7.6 amps in total. The primary, on the other hand, you can see there's only one winding, and that therefore can only have IR base, which is 1.9 amps. Note that the rated current is a thermal characteristic. So each one of these 6 coils can have 1.9 amps going through it without dissipating too much heat. So there we go. This is your example 1. The lowest number of current paths on the primary is 1, right? There's only got one of these paths that you can go down, and therefore the rated current for the primary is the same as what is specified at the datasheet, which is IR base at 1.9. Then the lowest number of current paths for the secondary in this particular example is 4. Therefore, each one can pass 1.9 amps. You can have 4 of them in. I've got 4 of them in parallel. Therefore, you can have 7.6 amps. Okay. So, parallel windings. Please note that on the same core are not separate inductances. It's just like having a thicker wire. So when you parallel windings, your inductance doesn't actually change, and that is our rule 2. Right? So if you parallel the windings on the same core, your inductance doesn't change, but your current increases. Okay. Note that you must always use the lowest number of current paths. For simplicity, let's say I have got an arrangement like this, whereby I have got 3 coils in parallel on the primary in series with a single coil. That means that this one is the bottleneck. Okay. So because it's a thermal characteristic, IR base is a thermal characteristic, this single coil is going to get hot. So although they have got 3 in parallel here, actually the rated current for this arrangement on the primary is still 1 times IR base because of this one down there. On the secondary, however, I've got 2 in parallel, which means that if IR base was in the datasheet defined as 2 amps, I've got 2 of them in parallel, I can pass 4 amps. Okay, so rule 2, when you parallel coils on an off-the-shelf transformer, the inductance stays the same. It's just that your current increases. Okay. So what are all the turns ratios that we can have? We have 6 coils. We can connect them any which way that we like, provided that we stick to the rules. Of course, the pin numbers will change, so please consult the datasheet. The ones that I showed you was for EFD15 and EFD20 range of flex transformers from Worth. However, many of these different combinations and permutations are not actually very useful or suitable for the DC-DC flyback that we're going to try. So I've looked at all the different combination and permutations, and these are the really suitable ones. You can have 5 to 1, 4 to 1, 3 to 1, 3 to 2, which is 1.5 to 1, 2 to 1. You can have 2 useful arrangements for flyback. You can have 2 that works well, and 1 to 1 you can have 3 suitable, useful winding arrangements, and we're going to talk about those a little bit later. Of course, if I flip my transformer the other way around, I get 1 to 5, 1 to 4, 1 to 3, and so on. Okay, and these will be used for the step up applications. So let's have a look at all of them. This one is 5 to 1. I have already given you the example of this one before, right? Then all I need to do is follow my rules, right? So rule 1, I'm going to make sure that the dot convention is followed. So create from, this is a 5 to 1. If I want to create a 4 to 1, all I have to do is take this one, put it there. It's now violating the dot convention, as you can see. So I need to have to flip that around. There we go. Then I stick that to there, and I've got myself a 4 to 1 transformer. Okay. Then 3 to 1. Now note that I've got spare windings. So in order to get more current on the secondary, I've put these in parallel with this one over here. And of course, if it's a step down application, we normally expect the secondary current to be higher than the primary current. And that's why I'm paralleling. If I can parallel anything, if I've got any spare coils, I put them on the secondary. Okay, there we go. So this is my rule 2. We've talked about that already. I've got 3 in parallel. Therefore, I've got 3 times the base current. Then 3 to 2. I've got 3 here on the primary. I've got 2 coils here on the secondary. Now, note that I've got 6 coils, so I've got a spare coil. So rule 3 says, don't leave the coil dangling. Right? Don't leave it unconnected, because you've got a chunk of copper in the middle of your core and it's just going to get hot. So you really must connect that. So there you go. I'm connecting this to there. And this is a good example of my rated current is only 1 times the base current. Even though I've got 2 in parallel here, the bottleneck is there. Okay. So what is the best way to parallel them? So rule 1, quick reminder, the stick to the dot convention. Parallel coils inductance stays the same, but the rated current increases, and you cannot have dangling coils. So on this one, you can see that the lowest number of current paths on the primary is only 1, even though 3 are paralleled here. So if I want a 3 to 1, right, this is not terribly useful for me, because these 2 are actually wasted. And it's limiting the current that is going down here, and is limiting the current over here. Current over here, it's only 1 times our base current. Again, same here. I've got 2 parallel there, 2 parallel there. I can't leave them dangling because it violates rule 3. And still, I'm not getting more current over there. So the best way to parallel them for, let's say, a step down application is to try and increase the number of current paths on the secondary, right? So I have a 3 to 1 ratio, and I have paralleled these 3. So I get 3 times the base current on my secondary, which is useful. So rule 4, parallel the coil such that you maximize the number of current paths in either the primary or secondary. And of course, for step down applications, usually we want the secondary current to be higher. So we have looked at 5 to 1, 4 to 1, 3 to 1, 2 to 1. So let us now look at 2 to 1. I said earlier on that we're going to have 2 different versions. So this is version 1. You can see that I have 2 coils in series, 4 coils in parallel. Therefore, I have the rated current on the primary and 4 times the rated current on the secondary. Then for 2.2 to 1 version 2, I now have 4 in the series on the primary and 2 in series in the secondary. So the current is the same, but note that this has got much bigger inductance and that's what we're going to talk about next. For those of you who downloaded the presentation earlier on, there was an error on this slide. So we have updated it. So if you downloaded it, more than about 10 minutes ago, please re-download it, because there's an error here. Thank you for Emil for pointing out the error, by the way. Now, So you can see that this one has got much higher primary inductance than that one because it's 4 of them in series as opposed to 2 of them in series. So we'll explain how to calculate the inductances shortly, but I've done all of the turns ratios apart from 1-to-1. So for completeness, I want to quickly do 1-to-1 as well. So finally, 1-to-1. Version 1, I've got the smallest inductance and highest current, you can see, right? Version 2, I've got medium inductance compared to this one, and medium current. And then finally, version 3, I have got the lowest amount of current, but the highest amount of inductance. So this is the 3 useful versions that I can have for Flyback. The whole objective is to try and find an off-the-shelf transformer so that I don't have to make a custom one. Okay. So the one thing that we haven't talked about is how is the inductance is impacted as you have got 1 in series, 2 in series, or 3 in series. Okay. How do we calculate the primary and secondary inductance? Well, the data sheet specifies something called inductance base or L base. In our case, for this particular part, is 3.4 microhenries. This means that we have 6 identical coils. Each one has got 3.4 microhenries. Okay. We already know that in the case of off-the-shelf transformers, if we parallel the coils, the inductance stays the same, but the current increases. What happens if we put them in series to get different ratios? Well, from school level physics, we know that actually inductance is proportional to the square of the number of turns, right? So in our case, L is K, a constant. We don't really care because L base is defined in the data sheet, right? But is proportional to the number of turns of a square. That's come from the original equation of the long solenoid. So if we connect 2 coils in series, we actually double the number of turns, right? But the number of turns is squared. So if I double the number of turns, then the inductance goes up by a factor of 2 squared, which is 4. Or if I triple the number of turns, i.e. put 3 in series, then the inductance goes up by a factor of 9 because it's 3 of them in series is squared and it goes up by a factor of 9. And that is how we calculate the inductance in series. Okay, so we know that L is a constant times the number of turns squared, right? In our case, let's say I have got 3.4 microhenries. If I connect 2 of them in series, I get this. And therefore, 3.4 microhenries times 4 gives me 13.6 microhenries, right? For those of you who attended our analog power supply design workshop, actually, we use this exact part, and we use 13.6 microhenries, and then we use the Bode 100 to measure it, and we'll see that it's exactly the same within measurement error. Okay, so we can connect 3 in series. That will be 3 times the n, and therefore that is 3 squared, which is 9, and therefore the inductance is 30 microhenries. You can see that if I start making coils in series, the inductance shoots up very, very quickly. So rule 5, the total inductance is given by, for primary, base inductance, which is specified in the data sheet, times the number of primary coils that you have connected in series squared. For secondary, same thing, L base, this, which is specified in the data sheet, then the number of secondary coils that you have connected in series squared. Okay, so as you can see that these rules are becoming really cumbersome, right? But I only have, was it 9 turns ratio? So I've stuck absolutely everything in a spreadsheet. You can calculate it by hand. I've given all the equations here so that if you have your own arrangement, you can work it out yourselves. But everything is in a spreadsheet. It's available for free, and you can download it from biricha.com/flex. So the part numbers are given here. Then I have got the turns ratios. You've got 5-to-1, 4-to-1, 3-to-1, 2-to-1, and so on. There's also a generic one whereby you can type in your own arrangement. So if you've got a different arrangement to what I've got, you work out the turns ratio that you want. This is calculated for you. Then you type in how many cores you have in series, how many cores you have in parallel, and the spreadsheet will calculate everything for you based on these part numbers. Okay, so For this particular case, which is a 5-to-1, the spreadsheet has calculated primary inductance and rated current, secondary inductance and secondary rated current. And so far, we have talked about pretty much all the parameters, right, with the exception of saturation current, right? So I've talked about all the turns ratios. We've talked about how you calculate inductances and rated currents with the equations. We have provided the equation and a spreadsheet. But the final thing that we need is the saturation current, because obviously you don't want to saturate your core when you design your flyback. That is also given in the spreadsheet, so you don't have to calculate it. However, for completeness, we're going to explain how saturation current is also calculated on these transformers. So how do we calculate our saturation? The datasheet specifies another parameter called ISAT base, or saturation current base. Okay. Note that saturation current, we're looking at peak and not RMS. So for saturation of this particular device is 4.18 amps. Unlike rated current, which is a thermal parameter, saturation is determined by the maximum flux that the core can handle, right? So if you go above, the peak of the current goes above, not the RMS, you saturate the core, okay? It's a little bit like a washing up sponge that is completely saturated with water. If you get a dry washing up sponge, right, and you fill it up with water, right, there comes a point whereby it is so saturated the water doesn't go in it anymore, right, and it'll go everywhere. So that, therefore, it's the peak that you have to use. So again, from school physics, we know that flux is proportional to the number of amp turns. So you can saturate, if you can saturate a core with one loop of wire, one turn, and 100 amps, you can also saturate it with 1 amps and 100 turns, right? So it's amp turns that matter. Now, consider ISAT base as the current that will saturate our core when we have the maximum number of turns. So if I stick all the coils, 6 coils in series, and then I pass current through it and see when it starts to saturate, that is what this number is. In reality, it's actually worked out in a different way. But for simplicity, let us just say, okay, I put all of them in series. At what point it will saturate? Because that gives me the biggest number of turns, lowest number of current. So if you only use, so that is for 6 coils in series. If I use 3 coils in series, I have halved the number of turns. Therefore, I can use twice as much current before the amp turns becomes to a level whereby it saturates my current. Okay? It's a little bit confusing, so I'm going to elaborate this on the next slide. So please remember that in a flyback transformer, when the current in the primary winding is flowing, there is no current flowing in the secondary winding. Stuff going on in the secondary is just that the secondary winding is open circuited by the diode. So when you talk about amp turns, there is no real contribution from the secondary on the amp turns for a flyback. So we are only considering primary current. At turn on, current flows. At turn off, for the windings, current stops. Now, from previous slides, we know that parallel coils on the same core don't increase number of turns, right? It's just using thicker wire. So we ignore all the parallel ones. We only look at the series ones. If we use all 6 coils in series on the primary, we can have our maximum number of turns, therefore minimum saturation current. There we go. At that point, primary saturation current is equal to ISAT base, and ISAT base is specified in the datasheet. If we have 5 coils in series on the primary, then we have only used 5/6 of the maximum number of turns. So we can have a little bit more current before it gets saturated. By how much? By reciprocal of that, by 6/5, and so on. So primary saturation current is 5/6 times I base, i.e. 1.2 times I base. And that makes sense. I'm using less number of turns, so I can have more current. So on the datasheet, ISAT base was specified at 4.18 amps. I'm using 5/6 of the number of turns when this was calculated. Therefore, 1/5/6 is 1.2. That times 4.18, that gives me saturation current of 5 amps, and so on. Okay, so rule 6, this is the final rule. For flyback transformers, ISAT primary, which you need for your design, and that comes out of a design tool, right, is 6 times ISAT base divided by number of coils that you have put in series. But it's all in the spreadsheet, so please use the spreadsheet. So if I have something like this, I have, this is a 3-to-1. I would not connect it like this, obviously, because it's not optimum, right? I would put these two on the secondary, but this is to explain how we're actually going to calculate it. These two, which are in parallel with this one, actually do not contribute towards pretty much anything, right? So this one has got 6/3 times ISAT base, because on the primary, you're only using 3 out of the 6 windings. This one has also got 6/3 times ISAT base, right? This one has got 6/1 because there's only 1 here out of the 6 possible ones that you can have. And this one is still 6/1 because they are not in they're not in series, they're in parallel. So you count the number of series coils and is reciprocal of that. So summary of rules. So far, we have given a full explanation of how it all works. The objective is to try to buy an off-the-shelf transformer along with all the other components as opposed to make a custom one. We have given all the necessary equations and where they come from. We've provided a flex transformer, which contains most of the useful combinations and turns ratios and connections. And we've got 6 rules to follow. You stick to the dot convention. When you connect the coils in parallel, the inductance doesn't change. It's just like using thicker wire, so current rating goes up. You can't leave any coils dangling. Parallel coils, you use such that you maximize the number of current paths, either on the primary or on the secondary. And for flyback transformers, at least, the saturation current on the primary is 6 times the base current, saturation, which is defined in the datasheet, divided by number of coils in series. Okay, so we can now look at a design example. As you may know, we provide a software called Biricha WDS, which designs the power stage and the control loop. And you can download that from here. You get 6 months for free if you're attending this webinar. And then we use our spreadsheet in order to work out if we can find something off the shelf. Okay. For those of you who don't know, Biricha WDS is an automatic click power supply design software. It allows you to stabilize the control loop, and it calculates everything down to component level, including all the stresses. We go through loop design and all of this in our analog power supply design face-to-face workshop. But for the sake of this short presentation, we're just going to use WDS and take the numbers that comes out of that. Then it calculates the size of the output capacitor, right, based on the ripple specification that we have. And finally, it provides everything that we need to select our transformer. So rated current primary, rated current secondary, saturation current primary, turns ratio, all of this comes out of the software, or you may wish to use your own software. And then we look at the spreadsheet to see whether we can find our transformer off the shelf. Okay. So when you open up WDS, the first page on the specification sheet, it looks something like this. We select flyback continuous conduction mode. I'm designing an isolated one. If you don't need isolated one, you can also design a non-isolated one. Then you type in your maximum nominal and minimum voltage. Then you type in your output voltage and output current. I am designing a 48 volt in, 9 volt, 1 amp out power supply. My switching frequency is 200 kilohertz. If you have flexibility on switching frequency, you can shift it a little bit down, you can shift it a little bit up, and that changes the peak current. So if you're saturating your core, if you up your frequency a little bit, the peak comes down. So maybe you can get away with tweaking it so that you can use an off-the-shelf transformer. The WDS is going to calculate the loop stuff, so we're not going to talk about that. And you specify how much ripple you want and how fast you want to recover from step. And based on that, WDS calculates your output capacitor. Okay, so step one, you're typing the stuff, and WDS calculates the stuff that you need. Then WDS calculates the turns ratio, right, based on the maximum duty cycle. That's at the bottom of the specification page, and you may have to go back and forth a few times in order to find the right transformer. Right? Flyback topology is quite forgiving with regard to the maximum duty cycle. Therefore, you can iteratively adjust this until you get the correct turns ratio. Maximum duty can be set to anything between 30 to 55, and you can still get reasonable results for the voltages and currents that we're dealing in a low voltage, low power DC-DC. So I'm going to start with 50% duty. WDS will design it for 50% duty, right? But if I cannot find my transformer, I may go back and change that, right? Remember that we can only have these range of turns ratios, right? So step two, for now, we just set the maximum duty limit to 50%, and you iterate and adjust until you find your transformer. So then we go to transformer tab, and here's where things get interesting. WDS has worked out that you want a turns ratio of 4.5 to 1. Of course, we can't have 4.5 to 1, right? So I've selected 4. You can type into WDS, no, I can't have 4.5, I'm going to have 4. So as soon as I type 4, note that the WDS has calculated primary inductance to be 300 microhenries. As soon as I type in 4, it readjusts it to 268 microhenries. So that is what I'm going to need. Then, it's worked out my saturation current on the primary. Yeah, I need that to select my transformer. It's worked out the primary RMS current. I need that to select my transformer. And it's worked out my secondary RMS current. I need that. This is all I need to go and find the correct transformer. So, on step 3, you iterate the reasonable turns ratios and look at the WDS values until you can find a correct part from the spreadsheet. So here is the spreadsheet. I've just zoomed into the bit which is suitable. So I've gone to the 4 to 1 tab. Then WDS tells me that the primary current of the transformer has to be bigger than 300 milliamps. And you can see here that these ones are all bigger than 300 milliamps. Okay, then WDS tells me from the previous slide that the primary inductance has to be bigger than 268 microhenries. You can choose a smaller one, but if you choose a smaller one, your flyback will go into this continuous conduction mode earlier, and the ripple will get bigger. So again, you have got a lot of flexibility here. If I can, I usually go one bigger because, oh, I do apologize. I do apologize. So I usually go one bigger because that reduces my ripple and it allows me to have a less noisy power supply. So, okay, now all of these fitted. Now, only out of all of these, only these 3 fit. Then I look at my secondary RMS current, and WDS says it has to be, the transformer has to have bigger than 1.4. And now all of these, only these fit. Okay, please go in this order, right? Because that's the way I have sorted the spreadsheet. Finally, saturation current has to be, for the part, has to be bigger than 300 milliamps, and therefore all of these fit. So the parts that fit all my requirements actually is that one. All right, we found the part. And then if you don't find it, as I said, you can tweak things. Maybe you can try 3 to 1 or 5 to 1, or maybe you can go and change the switching frequency a little bit. So the part, you have got a part that does not violate any of my requirements. So this part will work. And then all you do is you click on the spec. That opens the page that's got the data sheet of the device on Worth's website. There we go. That's the data sheet of the device. That's the footprint. Now you know what they mean with all of these parameters that they defined. Of course, everything is a data sheet, but we can also use hand calculation based on everything that we have discussed in this presentation. So if I want to do it by hand, just for completeness purposes, primary winding has got 4 coils in series, but only 1 current path, right? So the inductance is L base here times 4 squared, which is 345, just like the spreadsheet. R base is 800 milliamps. I've only got 1 current path, so it's the same as this term there. On the secondary, I've got 2 of them in parallel, so it's twice of that. And then the saturation current is 6/4, right? 6 divided by 4 times base, so 1.5 times 0.48, which is here. There we go. That is exactly the same as the numbers that you got on the spreadsheet. Note that there are no dangling coils. So I've connected this one so that I don't have a dead coil in my power supply, and the dot convention is not violated. So the transformer selection is complete. All we have to do is design the components for the control loop and so on. Again, you can do that yourselves. There are softwares online that will do it for you. WDS will, of course, do it for you, or you can attend our workshop. WDS you will see that has calculated the stresses on the MOSFET. This is your semiconductor, and on the diode. So you can go and buy the correct diode and the correct MOSFET. Then output capacitor. Again, all the stresses on the capacitor has been shown, and therefore you can go and buy that. Then WDS has also done current sense of slope compensation and control loop design, right? So we talk about all of this in our power supply design workshop if you need to get into details of how it's done. And finally, because this was a isolated power supply, WDS has, based on the optocoupler that you have used, WDS has calculated everything that you need in order to stabilize the loop. Or I know that Christoph Basso has got a fantastic book on the subject. I've read it myself, and the ISBN is given here. If you need to know about TL431s, isolated loop design, optocouplers, this is a very, very good book. So what's next? We are going to introduce our first online workshop from Biricha, and is to design flybacks really fast. The idea is that there are a lot of guys out there who are not power experts, and they don't want to be. All they want is the product to work, and is usually the flyback in the middle that is oscillating or not working, or they don't want to be dealing with magnetics, right? So it's got a hands-on element as well as being online. Its objective is to help electronic engineers with very little or no knowledge background in power supply to just get the thing out of the door. We talk about how you calculate everything on the flyback down to the very last component. You allow the engineers to dynamically change and therefore design their own flyback, as opposed to an application note whereby you whereby you just are stuck with the specification in the application. Okay, we have created these daughter cards with all the transformer turns ratios that we think is suitable for power for flyback applications. So it's all wired up. All you get is the 1.5 to 1 if you need, or 4 to 1 or 3 to 1. It's on a PCB, and then we have designed a flyback with this footprint here, so you can just put your transformer there off the shelf. You solder everything. I have so over-designed this board so that it doesn't blow up. All the RCD component, the clamp components, the snubber components, everything is out there. Typically, you're talking about 50 volts in, between 3 to 50 volts out at 10 watts. That's what we can do with these transformers. And we use WDS and flex transformer in order to not have to deal with a custom transformer. All the detailed material will be online, multiple design examples on workbook, and we are going to work out something with teachable.com, and you can buy the workshop from teachable.com. Okay, so to be kept informed, it's not on yet because I'm writing the material. Please register on our mailing list, which is on biricha.com/news. And that is the end of the presentation. I thank you very much for your time, and I wish you all the best.